on this computer. Okay, we are recording. Good. I don't know where we're recording. Okie dokie. You asked for, remind me, linearization nodes.
Or just kind of quick touch up on it, what the point of it is again?
Yeah, okay. Let me see. All right, can you see this? No, you can't, right? You can see this now, right?
Correct.
Yeah.
All right. The point is we have some nonlinear function, which means it's not a constant times a function of time. So we have some function that's like a square root or an x squared. And we know that we're going to operate at this steady state point. So we can evaluate that function and figure out how far from zero that is. But sometimes we're going to move away. And remember, all of our deltas are final minus initial. So final, where are we minus where should we be at normally? So this delta, which is x of t minus x steady state. If we know the slope at that middle point or that specific point where we're operating, that tangent line will exactly match the nonlinear function when we're at steady state. And as we get further away, as one our variable moves away, our x variable moves away in this direction, we'll use a slope to approximate that linear line. Because as we move away, that's this flat part of the triangle, and you multiply it by the slope to get this top part of the triangle. You add this part, 0 to here is the function at steady state. There up to there is your approximation, because you multiply the slope times the deviation. If you're close to steady state, the nonlinear and the linear are pretty close. As you get further away, they're pretty bad. And the other thing to know about is for two variables, you have a plane, so you have to take two derivatives. So if you have two terms in your function, two functions of time, like concentration of A and concentration of B, flow rate and concentration, temperature and concentration. If you have two things that are functions of time in one expression, you've got to take two partial derivatives. Okay? So Luis, let's see, flow in, flow out. You see, this is not a nice linear function of time. All these other terms are linear. Constant times a function of time. dHdt is just a function of time. 1 times the flow rate in. That's a constant times a function of time. This is where it gets bad, because we have to approximate this guy by taking the steady state function, taking the partial derivative. Now, again, I'll remind you, for square root of h, I don't remember the square root rule, but I remember to write that as h to the 1/2. And I know how to take the power, something to a power, I remember how to take a partial derivative or derivative of. So I take the partial, I expect that's a constant. If we actually know the steady state height, that's just going to be a number. And then this delta h. We plug all of this stuff in for this k squared of h term. You get flow in minus all this stuff. Now this is a linear equation. Constant function of time. Constant 1 times function of time. Constant plus a constant times a function of time. When we put it in deviation form, this constant is going to get canceled out. We write out the steady state equation. This goes to 0. This goes to steady state. This thing goes to steady state. So these guys are going to cancel when we subtract. We end up Fn minus Fn steady state is a deviation variable. Constant minus a constant goes to 0. Constant times a deviation variable ends up over here. So you end up with this nice linear expression in deviation form. Does that sort of make sense?
Yeah, so you're taking a nonlinear function or a nonlinear term and trying to make it linear.
Right. So let me go, I think, was it homework 10? I need to drag up the picture for this one. Hold on. Let me show you what it was. So the linearization homework. For this problem, we've got a tank. Some of the liquid bypasses the tank, and we get mixed in right here. We've got a reactor. So we have a volume here and a volume here. There's no reaction over here. The reaction over here is this crazy KMC. So it depends on the mixing rate and the concentration. So right away, we see that to a power 2.3. We know that's nonlinear, but it's extra nonlinear because it has two functions of time. So it's two variables. It's going to be double nonlinear. All right. So right away, we had some issues with some people having troubles on the mass balance, like what to even do. First of all, this doesn't seem to have any temperatures involved in any way, shape, or form. So you probably can avoid doing an energy balance. It looks like concentrations everywhere, so it'll be mass balances. We've only got one species, so we only have to balance that one species. It's not like A goes to B or B goes to C. We've got what, glucose coming in. It gets mixed here. It comes out. It gets mixed with this stream. And then it goes in the reactor and gets eaten up, I guess, or is it generated? What is the reaction rate? You're converting glucose, you're removing glucose, you're eating the glucose. So that's gonna be a negative reaction rate.
Right.
Now, when we actually go to the solution on this guy to set up the balances, the mixing tank's super easy. Flow in, which in this case is gamma times F. I think it said gamma was between 0 and 1. So you have, basically you have a special valve here that sort of splits that stream into partial. It could be like 0.1, it could be 0.5, it could be 0.7, but you set it up so that's an adjustable thing later on. So we have flow in. If that's volumetric flow rate, and this is moles per liter. If this is liters per time and this is moles per liter, this whole term has units of moles per time. And again, this is gonna be moles per time. If you look over here, the total amount of glucose in the tank is the volume times the concentration. So volume times concentration gives you moles. But when you take a time derivative of that, what's the rate of change of that? Volume's not changing, concentration of glucose is. So you get this accumulation rate. The accumulation rate has a units of moles per time. So all of my units, this term, this term, this term, these three terms, all have moles per time. The same thing on the mixing point. The only thing to remember on the mixing point, there's no volume. You got stuff going in, you got stuff going in, it mixes right there and stuff comes out. So when you write that mixing point, there's no accumulation rate, flow in, flow out. A bunch of F's are going to cancel. I forgot an F there. But you have a variable here that looks like it's an input, that looks like a state. This is going to give me some information that I need later on. The tricky part, actually this is not tricky. For the reactor, it's like a mixing tank. You got the same term, but now you got a different volume, a different accumulation rate for concentration of glucose, because we're looking at volume 2 times concentration of glucose in tank 2. You multiply those together to get the total amount of glucose in tank 2. What's flowing in, you got to keep track of the symbols. Well, we don't know what this feed is until we use this equation to solve for the feed up here. But we'll worry about that later. So flowing in is that concentration at that flow rate. Flowing out is that concentration at that flow rate, because it's well mixed. It said that on the problem somewhere. Everything's well mixed. This is volume 1, this is volume 2. They're both well mixed. The reaction rate on this problem said it's volumetric. So it was given in terms, the units on that reaction rate over here, moles per liter minute. all of my other terms are moles per minute. So if this is liters per minute and this is moles per liter, that's moles per minute. So because it's volumetric, we have to multiply by the volume. So we have that extra parameter. We have a reaction rate. We have all this other stuff in the reaction rate. We have a reaction rate coefficient, all this other stuff, but then we have to multiply by volume to get the total reaction rate, moles per minute. And that's where we start linearizing stuff. So this will get you a lot of points. Write the balances, get all the terms in the right spot, get the pluses and minuses. I would lose a point because I forgot an F right there. There's supposed to be an F in that term. But in general, this gets you, get the accumulation right, get the right symbols in the right spot, get the right terms flowing in and flowing out, get the reaction with the right units, get the mixing point equations, and you're in pretty good shape.
Right. What homework is this again?
This was homework 10. I think it was Monday.
I'm looking at it right now and I'm not finding it. Or is this, or did you just post the answers?
This is the part 2 solution. I posted I had a solution from last year, but it didn't have the right problems. I had this problem. I have a solution of this problem, which is a different problem. This is a different one too. This is interesting because it has two species. You have A and B. You have A going to B and B going to some other product. So you have a rate of conversion of A and you have a rate of destruction of, or conversion of B to something else.
So is B the plus sign in this one?
In this one, you've got two different species, so you have to do two different balances. So you have a balance on A and a balance on B. So here, A flows in, but no B flows in. So you have a concentration of A flowing in, and A flows out and B flows out. So you're converting some A to B. So this is the rate that you're converting A to B, and this is the rate you're producing B from A. See how it's negative here, and it converts to positive there? Then there's a second reaction. So B is formed in one reaction, and then B is converted to waste in a different reaction. So let me go back. So this is a totally different problem, but this is a little tricky, but not too tricky if you think about it. You've got A going in, you've got A and B in this reactor, two different reaction rates. This mass balance on A, and this is the mass balance on B. They look pretty linear except for this reaction rate term, because you have something squared and you have two variables of time multiplied by each other. Everything else is constant function of time equals constant function of time plus constant function of time plus constant function of time. This is the only thing that's changing, and it's nonlinear, so we have to take this apart, approximate it by evaluating it at steady state, taking the derivative with respect to CA, multiplied by deviation CA, and then derivative with respect to CB, multiplied by deviation CB. So mass balance A, mass balance B, both are nonlinear. Approximate the nonlinear, plug that into the mass balances again. Now it's a linear mass balance, but you have to get everything in deviation. So linear mass balance, write the steady state equation, subtract the steady state equation. Now CA naught minus CA naught steady state looks like a input. Flow times CA minus flow times CA steady state. The CA minus CA steady state is going to be a state variable. Constant minus a constant is 0. This constant times deviation CA is just a constant times deviation CA. There's nothing to subtract from it. This constant times deviation CB is just a constant deviation CB. So now it's all linear in terms of x1 dot u, x1, x1, x2. So when you rewrite this for state space, you divide by volume and you get something times x1 plus something times x2 plus something times u. You following that, Luis?
Yeah, I have it printed out too.
Okay. So do the same thing for concentration of B. You have the flow in, flow out, this reaction rate because you're producing it. Actually that's flow out and that's conversion to the other waste product. But the reaction rate that produces A or produces B from A is this term. You have to subtract the steady states. You get a bunch of stuff in terms of x2, x1, x2, x2. Collect all your terms. Write out your output equations. In this case, you're just measuring the deviation concentration of A and deviation concentration of B. So that's one of my state space equations, x1, x2, u. That's one of my state space equations, x1, x2, u. These are my output equations in terms of x's and u's. Those are my mass balances. So this is the problem we were just talking about, where you have that, or we started off talking about mixing tank, mixing point, and this guy, this reactor. So we have the mixing tank, mixing point, and reactor. We have to linearize this nonlinear term here. And again, evaluate at steady state, partial derivative with respect to deviation variable 1, so m, partial with respect to m times change in m, partial with respect to c sub g2 times deviation cg2. Now this is our linear tangent function. It's actually a tangent plane because it's a function of 2 different variables. Plug it back in. We've got linear equations. But we don't, this one was tricky because we didn't know the mixing point value. We have this C sub GF. We don't know what this concentration is going into the reactor. But if you know the feed concentration and you know the concentration out of the mixer, you can figure that out from the mixing point equation. So you end up writing everything in terms of deviation, everything in terms of x1, x2, u1, u2. The same thing for the output equations. You can measure one of the concentrations, you can measure another concentration. Let's see. I think this is the problem we haven't talked about yet. This was on the homework that you did for Monday. It also has a mixing point. It has a nonlinear reaction right here. Got a question, Luis? I mean, I keep talking, but.
Well, I'm listening. I have it all printed out too, so.
Okay. So this one looks like energy, but it also has a reaction rate with concentration. So it might be both energy and mass. So it looks like we have something in there. With concentration and temperature, it looks like the reaction rate depends on concentration and temperature.
So it's gonna be energy and mass balance?
So yeah, we gotta do both. And there's a mixing point. So constant volume, we've got energy that we can adjust here. We've got the temperature we can adjust.
So 2 energy, 2 masses?
We could do an energy balance and a mass balance on the tank or the reactor. We could do both energy and mass balance, but I'm gonna tell you, this one ends up, we only need to do an energy balance because we only care about the product temperature, not the product concentration. If you look at it, all we need to do is know what the concentration is inside the reactor, because we have to model this measurement. We don't care what the concentration is actually leaving. I mean, it doesn't hurt to have an extra equation, but for this problem, we don't have to have that extra mass balance for the mixing point because there's no product concentration that we care about. We just care about the reactor concentration coming out right here.
Correct. We only have one sensor? or two, one.
Well, we have, for the concentration, we have one sensor there, but for temperature, we have the mixed temperature. So you have temperature that bypasses, and you have energy that goes into the reactor and then comes out. I don't see a heat of reaction in here, so we're going to ignore it, I think. That's 10. All right. It looks like somewhere in here, did I say no? There's no concentration coming into the system. So you could write F times C naught, but I just put a 0 in there. So we're doing a balance on the concentration of plankton in this case. Flow in, there's no flow in, there's a flow out. It said it was 2F, and then we're growing it, so that's the reaction rate to grow it. We're doing an energy balance as well, so we can track the temperatures. We know the flow rate times density gives me mass per time. So if this, oops, that's mass. Mass times density gives me, I'm sorry, that's volume per time times density gives me mass per time. The units on CP are joules per kilogram degree.
Right.
So when we multiply mass MCP delta T, MCPT, we get joules. But this is not mass, it's mass per time, so this whole term is joules per time. So joules per time flowing in, joules per time flowing out, and then Q, because we can heat it up with steam, I guess it said. What does it say?
Well,
Somewhere on there it says, steam heating is available to the reactor, Q, blah, blah, blah. So we can put Q in. So we can heat it up. We got energy flowing in. We got energy coming in from the steam. We got energy leaving. And we're avoiding the reaction rate. The reaction rate doesn't heat us up. A lot of times in aquatic systems, or you don't have an extensive heat of reaction, at least not enough to worry about. So this gets you a lot of points because you got your mass balance, you got your energy balance, you got all the right terms, everything's in the right units. If you look on the problem, Q is given in, oh, I don't have units on this one. That should be joules per second.
just assume that.
So that's, so all of the terms in the energy balance are joules per time. All the terms in the mass balance are moles per time. We see this nasty reaction rate term, but we have to linearize it. The constant, the derivative with respect to CF, derivative with respect to T, and then you write this nonlinear reaction rate or mass balance with all this junk in it.
What you said the first one was respect to?
The first one here,
Yeah.
you have two variables, T and CF. So we have to take this guy with respect to the concentration of F. So what's the concentration here? VKT steady state, negative times -2, CF to the -3.
Right, right.
So partial with respect to CF. Then a partial with respect to T, you're basically going to get all of this except for T. So that's my delta CF, that's my delta T. And again, this, if you're a visual person, this is approximating, we've got this nonlinear function of two variables in 3D space. It's like a nonlinear surface. This guy is a nonlinear surface. Reaction rate is the z-axis, T and CF are the x and y. This guy is a tangent plane. Not a tangent line. It depends on how far from the steady state concentration, how far from steady state temperature you are. So you're making a flat plane approximation that touches that nonlinear surface and approximates it in the CF and T direction. When you're at steady state, it exactly matches it because this is perfectly the nonlinear term. You take all that linear stuff, Put it back in the nonlinear equation. Now you've got a linear differential equation. Go through the whole state space or the whole deviation variable thing. Linear equation, linear steady state equation, subtract, you get deviation variables.
Yes, yes, correct. And use.
You see how these terms here, CF of t minus CF steady state, or I mean, I'm sorry, C sub F of t minus C sub S steady state.
And that gives you the state input
That looks like a state variable.
variable, sorry.
We talked about this too. If you have mass and energy balances, anytime you have a DDT of a variable, that's going to be a state for these ODE systems. Like concentration of F, we know that that's going to end up being, this rate of change is going to end up being x1 dot. So that means deviation CF is x1. The same thing with rate of change of T, temperature, is going to be x2 dot.
Right.
So when we change all the variables, it's just a bunch of x's and in this case, just x's. U doesn't have any effect on the concentration.
Mm-hmm. Use measurement, right?
Y's are measurement, U's are inputs.
There we go.
On the energy balance side, the energy balance is all linear. You have the feed temperature and the steam heat and the flow out. So the feed temperature is an input. The steam deviation is an input. So if you want to have some effect on the concentration, this temperature can mess up this feed temperature can mess up the regular temperature in the reactor. The steam can have some effect on the temperature in the reactor. And then the temperature can have some effect on the rate of conversion or rate of growth in the reactor. So these two differential equations are coupled, and you can drive them or change them by changing U1 and U2. But this guy is all linear. Constant function of time equals constant function of time plus constant function of time.
Which two are coupled together?
We have two balances. In this case, we have the concentration balance and the energy balance.
Right. If you adjust the measurement, you can affect the output. Or
you adjust the input, and you can affect the states, and the states will give you the output.
right. So
You can simulate the system by running out these state equations, but usually we can't measure all the states. A lot of times we'll have many state variables, many balance equations, but you can only measure like the temperature.
Mm-hmm.
So you can still simulate all those states. So this linear equation, this is a linear equation in terms of U's and X's. This is a linear equation in terms of U's and X's. So we can simulate how things, if we know the initial conditions for the concentration and temperature, and we know how the feed temperature and the steam changes with time, this is two differential equations. But then the output equations tell us what we can actually observe in the real system.
Right.
So the output equations, you can measure one of the deviation concentrations, which is just a state. You can measure the deviation product temperature. But now we have to go back. This is where it got a little tricky. We don't know what the product temperature is. In this case, the product temperature depends on the temperature coming out of the reactor, which is state X2, and the temperature coming in from the up here, the feed temperature. So T naught and T mixed together to give us TP. So we've got most of the problem at this point. We've made the mass and energy balances, we linearized, we got it in state space form, but we don't know this product temperature. So we have to do the mass balance or the energy balance on that mixing point. What's flowing in? T0 flows in, the reactor flows in twice as much as the feed, because this is not half and half. This is one third of the raw temperature and 2/3 out of the mixing tank or the reactor. What flows out? All of this at the product temperature. So once you cancel all the F's and rho's and CP's, you're going to end up with the product temperature depending on the deviation. The deviation product temperature depends on the temperature coming out of the reactor and the temperature fed into the system. You write the energy balance, you write the steady state energy balance, you subtract and you group your variables. T0 of T minus T0 of steady state is an input. T of T minus T steady state is a state. TP minus TP steady state. We define that as one of our output variables that we can measure and observe.
Makes sense. And the last one was for the mix point?
Yeah, this is the last one's for that mix point.
Why would you have a bypass there? Is that just to maybe cool it down after it leaves?
Various reasons. So a lot of times, yeah, you get different dynamics. Sometimes you need to react some, but you can
Prevent it from too viscous or something like that?
Yeah, it gives you more flexibility in how you operate the system. And you get a different response. If you saw from today in class, a lot of this stuff goes back. This class, like I keep saying, ideally you'd know everything at the same time, but we have to keep growing our knowledge. Today we talked about lead lag systems, where you have the bypass and the reactor, or the bypass and the tank. You get a different response to a step input. Instead of being a nice exponential curve up, you get a jump and then a curve. And sometimes that's desirable.
You also have a lot of the vocabulary written in the big packet, right?
Oh, I'm not sure how much vocabulary I've got in there, but you may want to look at, I think I've got a easy, this is a nonlinear, simpler, easier bypass problem. It's similar to what we just did. Concentration coming in, most of it goes to this volume. Some of it goes around, and then we measure the deviation concentration here.
Right.
So that's a little bit simpler because there's no energy balance to confuse you. And this has a bunch of units written out for the most part. And it goes a little further because it takes it writes out the balances on the reactor mixing point, puts in numbers for some of the terms. This is something we haven't talked too much about in class. To actually find the steady state concentration, you take the balance and set the concentration rate of change to 0 and solve this equation. So this is the nonlinear balance. This is a linear form when you put the linear term in there. Right at the linear term, linear equation. Maybe this does go to state space. Oh, this goes to state space, but it's sort of boring because there's only one state and one input and one output. So when you look at the state space equations, you've got one state equation. One state equation that depends on X and U, and one output equation that depends on X and U.
Right. Well, it's a simple system too.
Yeah, it's a little bit simpler. So but for state space, usually we end up with like a 2x2 or 2x3 or 5x5 or whatever it is.
Right.
And remember, your matrices should stack. Like in A and B have the same number of rows. C and D have the same number of rows. A and C have the same number of columns. B and D have the same number of columns.
Gotcha.
We're not doing Laplace transforms. So from here on, it takes linear equations and goes to Laplace and does some stuff with it. But that's what we're going to get into before next Friday. So you take your linear equations, Laplace transform, do some algebra. Now you've got a transfer function that relates U to Y. And this almost looks like our lead lag system.
It is.
You can manipulate it around to look like this is our lead lag. So you have to adjust this thing into that form. So you get a gain, time constant, lead time constant. Actually, that's where you end up. But you see how much algebra it takes to get it from this. If I show you step by step to get it, we want it to look like this. We started here, so we have to do a bunch of steps to get it there so that you have it in the same form. But again, I should just be quiet because this is not relevant for Friday. This Friday.
Just the stuff we were talking about previously.
Yeah. Just the mass and energy I said. Let's see. Here on page, what is this, 40? You may want to review these chapter 4 in the handout.
Mm-hmm.
Most, I mean, definitely before Friday, but some of this dynamic modeling gives you some hints or procedures. State space gives you some hints. So those two segments, linearization. Some of this other stuff is important for next Friday. Here's another lead lag system. Flow in with a bypass, this time with an energy balance.
Right. So lead lag going to be on this quiz Friday, or is this not on the?
Well, we're not going to talk about it. Lead lag is a specific type of differential equation. It's a first order system with a pure gain as a bypass. Right? The stuff that we're looking at is actually more complicated because you have multiple states, you have a bypass, you have multiple outputs. So lead lag, we're starting out, we are writing the equations and putting them in the right form, but we're not worried about the response of this system yet. Does that make sense? So we're writing the equations that detail how the concentration and temperature could change over time. When we actually get to the lead lag stuff, what we're doing now is taking these systems, taking a set of differential equations and looking at different input sequences. If we put a step in, if we put an impulse, if we put a ramp, then switching to pure capacity or lead lag. So, and lead lag and first order and pure capacity are just special cases of what we talked about last week with Laplace transform of differential equations and partial fraction expansion. It's just looking at common types of problems you might run into because chemical engineering, a lot of times you'll have a tank or a mixing tank or a simple single reactor and it looks like a first order system. So this is just trying to show you specific cases. And then make little changes. Lead lag is the same, but it's got the bypass. So I won't ask you stuff like about xi and tau and how this response goes, but I could give you a differential equation that I expect you to Laplace and take it back to the time domain a week from Friday. It might be a lead lag. It might be a second order, like a two tanks in series thing. I won't ask you about the specifics in terms of like xi and tau and zeta and the other terms, but you should still be able to do Laplace transforms of the differential equations.
Okay.
Good questions, Luis.
Thank you. Trying to prepare.
Other questions, anybody else? Or you got other questions, Luis?
I'm still thinking. I had a couple. Most of them were answered.
Let's see.
And this is going to be posted on YouTube, right?
I hope so. Unless there's some sort of technical failure on my end. I've been recording it, but I got to figure out how to upload it.
Okay.
So in the real world process, when you're running a trial for whatever reason, when you're trying to adjust parameters, are you just basically opening and closing valves in the chemical process?
It depends. The stuff that we did in lab a week or two ago, that first order response, k-tau alpha stuff.
Yeah.
Something like this. You have an idea. Sometimes you need to get a dynamic model for your process. So you could go in, if you don't have any idea how to model it, if you just change one of the valves, you can look at the response, and that'll tell you how much it changes. The problem in a real process, you have lots of stuff going on. You have disturbances, things upstream that are upsetting your process.
Right.
Stuff. So it's hard to get everything at steady state so that you can do this kind of change. If you can, that's great, but a lot of times it's hard to do that. And we'll start talking about other processes, like the lead lag system doesn't look like this. It jumps and then goes to a step. Second order system doesn't have a kink right here. It's sort of a smooth transition.
Is that why the name of the lead lag? It doesn't lag. It leads higher lag essentially.
The problem with, again, this is one of those issues. The lead part comes out like in chapter 9 when we get to frequency response. We're not there yet. There's a behavior. We start looking at these linear systems. If we put a sine wave into them, they act funny at different frequencies. You ever seen the Tacoma Narrows video where the bridge collapses with the wind?
I think so.
Different dynamic systems, if you put an input at different frequencies, sometimes weird behaviors emerge. So that's the lead behavior is for some lead lag systems. It looks like the system is actually ahead of its, you put a sine wave in and it looks like the response is actually ahead of the sine wave. So that's why it's called lead. It has nothing to do with what it's all frequency stuff that we're not there yet.
What was the video?
Which video? The
lead lag?
Lead lag? Or Tacoma Narrows. Which video?
Yeah, that one. You said that's the name of it? Oh, the Tacoma Bridge where it's like moving up and down. Yeah.
Yeah.
I've seen it. Bunch of sine waves. So this is the same like it's like the way an alternator works in a sense. Is that if you know how that functions or not?
An alternator? You mean like in your car that generates electricity?
Right.
I thought that was just a little electric motor driven as a generator.
I think that's what it is. Yeah, I'm thinking of two different things probably then. That's exactly what an alternator is. It just creates more power. It's just a small generator.
Right. So it takes some of the mechanical power. Looking for other examples. We went over this one in class as far as mass balance goes. Got a mass in, mass out reaction. This is a mass and energy in a tube. Yeah, we're going to get to this later on, usually closer to drop day. This frequency stuff is imaginary numbers and more algebra.
Right.
Let's see. So this is more review for the midterm, drawing control loops, transfer functions. I don't think there's a mass and energy balance in there. That's a little more, this is more like for the final. But we had some examples. It was homework 6 was mass balances, mass and energy balances.
That's like the basic stuff.
That
was the first one, I think.
First time we saw mass 6. Yeah. So you got reaction rates. Everything's linear in these cases. So you just have to do balances on the different terms. This problem had a mixing point to get the product concentration. So right, 3 dynamic balances, 1 algebraic balance. The mixing point, you have to make that volume. The volume of mixing goes to 0 because it's instantaneous. Whatever flows in is mixed and flows out. And the hardest part on this, once you get these equations right, you have to go through the steady state to change the variables and then write them in state space. You see, I have 3 states and 1 input. So I stack my A matrix is 3 by 3, my B matrix is 3 by 1, C matrix is 1 by 3, and D matrix is 1 by 1.
Yeah, I have a lot of that stuff printed out. So I'm gonna review it,
Okay.
run through it a couple times so I get it right.
Once you look at enough of these, like the overall handout, you start getting in the problems. And there's a bunch of mass. Here's an energy balance. You got stuff flowing in, so it flows in and flows out, but there's some heat transfer across the wall. There's heat coming in here. There's a blower, so there's air coming into the stream in here is different from the air stream in the reaction. So you have a process stream that's heating up. You have air coming in at one temperature and leaving at another temperature. You're generating heat. The combustion heat is going into the process stream and out to the environment. So just getting all those terms in the right spot can be tricky or can help you get a lot of points.
Mm-hmm.
We do this one. This is one we talked about earlier. Balance on A, balance on B, a reaction of A to B. So it's going away from A, creating B, and a reaction for a bug, mosquito in my house. This is a neat one. 2 different terms, 2 different volumes. You got stuff flowing in and stuff flowing out. From this volume, you also have 2 flows in because you have stuff flowing in at temperature 0, but there's also stuff flowing in at temperature T2. So you have 2 different flows in and you have 2 different flows out. It flows out at T1 and it flows out at T1. And then on this side, this reactor has energy in from the flow and energy out from the flow, but also energy out to the environment. So you have 2 energy balances to deal with.
And 1 mass flow rate?
There's nothing about mass on this one. There's no concentration change, so it's all.
Oh,
if
okay.
you have constant flows and no concentration information, I mean, you could still do it, but you just have to make up some variables and say the concentrations are all going to be constant. This one looks like another energy balance. Stuff comes in, you have a volume up here to do an energy balance on, you have a volume down here and an energy balance on. It looks like, what is Q2? So you're chilling this side. So you have flow in with energy at T0, flow out with energy at T2, and energy out due to chilling. We have flow in at energy T0. We have flow out at energy T1. So we have energy balance on this reactor or this whatever it is, but there's energy transferred from the outside at this nonlinear rate. And then to figure out the product, you have to do a mixing point balance. So you energy balance on V1, energy balance on V2, energy balance on the mixing point. So just going through these problems and thinking about what balances do I need to write. Look at the picture, look at the words, try and figure out what the basic balances are. It's usually just on the volumes and on the mixing points. We've talked about that one. Did we do this one? I think we did this one.
This is a homework, right?
Yeah, it's a homework problem. So we have linear reaction rates. So 3 balances and a mixing point balance. So after you look at a bunch of these, they all start to look pretty similar. You just start doing your balance on this volume, either in temperature concentration. This is one of my favorite problems.
Gut and blood. Huh.
Metabolism of ethanol in the body, in your blood. So you have a volume of liquid in the gut at a certain concentration. You have a volume of blood. There's a transfer rate from the gut to the blood, and there's a reaction rate from the blood into other values. So there's a diffusion across this barrier. There's no flow between the gut liquid and the blood liquid, but you assume there's a barrier between those two, and it can diffuse across that barrier.
Mm-hmm.
So you got 2 different balances to write: the concentration of ethanol in the gut, the concentration of ethanol in the blood. You can figure out how much ethanol is flowing in due to this flow rate and that concentration. You can figure out how much is flowing out due to that flow rate and that concentration. You can figure out how much you're losing from the gut based on that diffusion rate. You can figure out how much is going in the blood volume based on that diffusion rate. And this looks a lot like HA delta T, right? You've got a fudge factor and area term, constants, and this delta. If there's more concentration here, it's going to push ethanol into the blood. If for some reason you have a bunch of ethanol in the blood, this term is going to go negative, because if this is usually like 10 and 5, so it's positive. So that means we're assuming it goes this way. If somehow like you injected ethanol straight in your blood, you get really high blood alcohol, like 20, and this is still 10. 10 minus 20 is going to go negative, and the arrow, you're going to use the backwards arrow. I mean, you don't have to do anything. The equations automatically take care of it. Sometimes you make the assumption it's going one way, and it usually does. But if it ever gets messed up, it could go the other way, because this delta term goes negative. And you don't have to do anything at all. The equations will solve it.
Yeah. Okay.
But I always draw these diffusion terms like that, HA delta T, or diffusion of concentration, because it could potentially go backwards. But you have to read the problem and make your assumptions about which direction it's going. It's going to be positive. If it's showing up, it's positive in this volume. If it's leaving, it's negative because it's being pulled out.
Okay.
It can't be positive in both, and it can't be negative in both. And usually you can figure out which way it's going based on this is probably higher than this, so it's probably going from G to B.
Alex, do you have any questions?
I'm just listening, taking notes.
This one was a little tricky. You've got 2 different offices, temperature 1 in the one area. So you've got a mass of air over here, and you've got a mass of air over here. This is at temperature 1 in volume 1. This is at temperature 2, volume 2.
Mm-hmm. Were there 2 windows?
Right. So energy's coming in. It looks like we have energy is removed. Where's Q? Do we have a Q?
Yes. Who? No.
Is it not in the words? So you have a chiller here. So you're taking energy out here. So you basically do an energy balance. There's no flows though. You only have energy coming in from the outside, energy coming across the wall, and energy leaving due to the chiller. And on this side, you have energy coming in from the outside and energy leaving due to that transfer across the wall. So this is an energy balance with no flow in and out. You have fewer terms. It looks like a two mass balances and a mixing point. Just looking at the picture. All right, so there's a few problems. There's some more recent problems we'll look at potentially.
Yeah, I'll run through a couple of them, and you said just email them to you, scan them?
Yeah, you do your solution. I'd prefer that you send me PDFs.
Yeah, I'll do that.
If you do cam scanner, I like looking at those because sometimes if I'm trying to look at it on my phone, it doesn't pick up. I can't zoom in on the images, and the images look, if you just take a picture, it looks terrible.
Right.
So the PDF helped me a lot better.
Okay.
Any questions, Alexis? Nothing?
I'm good. I'm sorry. I'll probably email you with questions later.
Yeah, you guys enough of those already.
All right.
Okay, guys. Thank you.
All right. Hopefully this helped. Talk to you later.
All right, you have a good one.
Bye.
Thank you.